Hello, calculus folks. We are going to take a look at that example we were working on Wednesday. And I want to finish that for you before we start talking about some of these harder substitutions and how we can think about some of these harder substitutions in maybe a more kind of concise way, and a way that kind of makes sense, hopefully, or more intuitive sense. So we were looking at this question, which is finding the arc length of this sideways facing parabola from 0, 0 to 1, 1. And I showed you the setup process for setting it up not only with regards to dy, but also with regards to dx. And essentially you kind of boil these problems down, and eventually you want to kind of choose one of these paths. So you look at both of the options that pop out, you check to see if they're linear, you check to see if there's 3 terms, so that maybe you can turn this into a perfect square. But most of the time, those 2 other avenues don't present themselves. So here we ended up with 2 square roots that were neither linear or perfect square trinomials. The one on the right, I suspected that we would be able to potentially work on that with substitution, and it turns out that you can. It just turns into a new question that we haven't looked at the technique to finish off that integral. So I'm talking specifically about this one over here. You know, we got to this one, I suspected that maybe we could try a substitution and get this one to work, but it will boil down into a rational kind of integral, and we haven't talked about how to tackle a generalized rational integral yet. That's the topic called partial fraction decomposition, and that's going to come up after reading week. So we'll take a look at how to deal with that problem a little bit later. So for now, can't really use this one over here. We don't have the techniques to actually solve this particular integral. So what we did was we kind of rolled, chat told me to roll with this integral here, 1 plus 4y squared. And what we did was we kind of thought about, there's 2 terms and they're both squared, and I was kind of thinking about the Pythagorean identity here, right? If I could somehow make a substitution to potentially make this work. And so we kind of settled down on a substitution. We took I believe one of the 1 plus tan. So we kind of were like, if I can change 4y squared into tan squared, that would be helpful, because that'll help us remove the square root. So that's where we started with our substitution. We said 4y squared should be equal to tan squared, and that way we're going to get a secant squared under the square root. So we found a relationship for y, found the derivative, and then that allowed us to exchange the differential dy for something else that had a dx in it. Okay, so the substitution that we used was we replaced 4y squared with tan squared, replaced dy with this 1/2 secant squared dx, and then we went ahead and tried to simplify this integral. So simplifying, we got rid of the square root, combined our secants together, and we ended up with this integral here that is 1/2 secant cubed. Now, we ended this lesson on Wednesday by saying that we had already done an integral very similar to this. We can apply the reduction formula for secant as well, if you don't want to just kind of dial back into your notes. But in the integration by parts section, we were talking about secant reduction. So we developed the secant reduction formula. So that's one that you should probably put on your little cheat sheet of things to know. And we actually did solve secant cubed together as well. So we know that the general antiderivative of secant cubed is given as this, my apologies, is given as this expression down here at the bottom. Okay, so this expression down here is the general antiderivative for secant cubed. We're going to grab that information, take it back to the example we were working on. We're just going to get rid of the plus c. So when we're working with integrals with bounds, we don't need that plus c. It's going to end up canceling anyway. But we just need a antiderivative according to the fundamental theorem. So this should become 1/2 times that expression that we just grabbed from that integral that we had done before. So just let me copy that down. So 1/2 secant tan plus 1/2 times logarithm of the absolute value of secant x plus tan x. Okay, and we just have to be mindful that, one, we need to get y back in here because our original integral was 1 plus 4y squared. It was with regards to the y variable. And then we're also going to have to evaluate that between our bounds as well. Okay, so this kind of removes the integration symbol and the differential for us. We kind of know how to move forward, but we have two more last steps just to finish this up. We need to get y back in. And two, we need to evaluate it at the bounds. Okay, so let's scroll back up to the information we have here. We have y is equal to 1/2 tan x. Okay, so we know that y is equal to 1/2 tan x. But what is x? It would be, I see a lot of x's here, right? It would be much more helpful, I think, to have an expression to actually solve for x in this expression that we found above. So we know that in red, try one more time. We know that 2y is equal to tan x. And if we apply arctan or tan inverse to both of these sides, that will solve for x. So we have that tan inverse of 2y is equal to x. Or equivalently, if you like the arctan notation, that's usually my preference, we have the following. Okay, so these two things are the same thing, right? Tan inverse and arctan. So that gives us a way to move forward for step number 1 and return y back into the expression we have. I'm going to go ahead, I'm going to multiply this 1/2 through the brackets as well. So we should get 1/4 secant of arctan of 2y, that's ugly, times tan of arctan 2y, plus 1/4, and we'll get logarithm of a similar story here. So secant of arctan 2y plus tan of arctan of 2y. And of course, evaluating this, now that y is back in, well, we're just going to evaluate this between 1 and 0. So it's kind of a nasty expression that we get here. And this is the reason why, I mean, some of these we can do fairly easily, like this, tan of arctan, those are inverse functions, so this is just 2y. Tan of arctan, well, we know that's just going to be 2y because those inverse functions will undo each other. But it's going to be these other expressions here, that are a little bit trickier to get into exact form. So I'll show you kind of quickly how to set up this, or refresh your memory. Hopefully you have seen this before in derivative calculus, is usually where I will cover these kinds of simplifications. But let me just kind of simplify, and then we'll kind of set up a way to get rid of this secant arctan thing. I did try to put some of this stuff into the calculator, but the calculator unfortunately didn't return back exact answers. So the calculator is going to give you a good decimal approximation for some of the values that we would get. It's just unable to get the exact answer. So we might have to go to, if you're kind of struggling with this particular step, you may have to go to the integral calculators to kind of see how they do their backward substitution, if you're unable to get a hold of me for questions. Okay, so in blue, I'm just going to, I want to think about this expression. We need to simplify secant of tan inverse of 2y. Now, secant acts on an angle. In fact, secant of some angle is defined to be the ratio of the hypotenuse over the adjacent side, I believe, right? Because it has to deal with cosine. So secant acts on an angle theta, let's say, and in fact we know that secant theta is equal to the hypotenuse over the adjacent side. So we do need a little bit of that knowledge from our preliminary pre-calculus or trigonometric exploration. So yeah, keep that kind of in the back of your mind here. We are going to use that in a second. Okay, so let's pretend that arctan of 2y is actually an angle, which it should be, right? Arctan should act on a length and return back an angle. Okay, so we're going to pretend that theta is actually equal to arctan, so that what we're looking at is secant of theta, okay? So we're kind of making a substitution in, we're kind of thinking about replacing this with some angle, I'm calling it theta, and we're going to try to set up the right-angled triangle that's associated with this particular problem. Okay, so we're going to draw a nice little right-angled triangle here. We'll throw in our reference angle theta. So this is the arctan of 2y bit. And I'm going to grab this relationship here because the 2y here is going to be important. So let's grab arctan of 2y is theta. We know that 2y is equal to tan of theta, and that's important. So we know that tan of theta, tan acting on this angle, should be 2y. We know that tangent is opposite over adjacent. Okay, so tan of this angle has to be 2y. That's how I know the two side lengths of this particular right-angled triangle. To get the last side length, what we need to do is apply Pythagorean theorem. So we're going to add these up, the square of these values. So let's call this the hypotenuse, and we know that hypotenuse squared should be 2y squared plus 1 squared. Okay, so hypotenuse squared is 4y squared plus 1. And it's not a coincidence that the hypotenuse turns out to be the original integrand. Not a coincidence. That is usually the case here. Usually you're going to find that this original integrand is going to pop up as one of the side lengths on this special triangle. Okay, so that's really the information that we need. We know that this side length over here is 4y squared plus 1 underneath a square root. Of course, taking the positive square root here because we're working with a length. Now, what we would like to do is find secant of that angle, right? So in other words, I'm kind of thinking back to here. I want to simplify this expression. So in other words, I need to simplify secant of theta. What is secant of theta with regards to this particular right-angled triangle? Okay, secant theta is hypotenuse, like we said, hypotenuse over adjacent. So secant theta is going to be 4y squared plus 1 under the root, divided by 1. So secant theta turns out to be a really lovely expression, a little bit easier than the expression we had up here. So I'm going to go ahead, I'm going to copy this line, and I'm going to perform that substitution so you can see, or it's not a substitution, it's more of a simplification, I would say. So let's go ahead, paste that in, and everywhere we see secant theta, or secant of arctan 2y, we're going to put in 4y squared plus 1 under the root. Okay, so this simplifies to 4y squared plus 1 under the root, then multiply by 2y. 1/4 logarithm secant of theta again right here. So this is going to simplify to 4y squared plus 1 under the root. And then we have a plus 2y here at the end. So it still looks kind of nasty, like it's still a kind of a gross expression. But hopefully subbing in, like the value of 0, hopefully 0 will clean this expression up a little bit. But now the idea is to sub in y equals 1, figure out what that number is in exact form, sub in y equals 0, figure out what that number is in exact form, and then find the difference of the endpoints here. Okay, so subbing in y equals 1, we're going to get 4 plus 1, which is square root 5, times 2 plus 1/4 logarithm y is equal to 1, so we get root 5 plus 2. Okay, so this line, or all of this right here, is y is equal to 1. Then we need to subtract y is equal to 0. So we get 1/4 square root 1 times 0 plus 1/4 logarithm square root 1 plus 0. Okay, so all of this here is me subbing in y is equal to 0. It turns out that all of this over here just becomes 0, right? This expression here goes away because we're multiplying by 0. And then this expression here, we end up getting the natural logarithm of 1, which is equal to 0. So that expression disappears as well. So we're going to be left with all of this stuff that we have here in the y equals 1 section. And simplifying that, we're going to get square root 5 over 2 plus natural logarithm root 5 plus 2 over 4. So that would be how to finish up that particular integral and get what we call an exact answer. If you, so let's say we're working on a Moodle quiz, and the Moodle quiz says, put your final answer in decimal form, right? Decimal form to 2 decimal places. You could probably come up here and not have to worry about drawing out the right-angled triangle. You could make your substitutions in here for, 1 and 0. You could just sub in here. And then use your calculator. Your calculator can simplify something like this. It will simplify something like secant of tan inverse of 2, and will give you a decimal number. So that's totally a legitimate way to get the decimal representation. It's just that your calculator can't get you to the exact answer. If we're doing something like WebAssign, and WebAssign asks for the exact answer, you're going to have to go through this process of setting up that right-angled triangle and potentially trying to simplify these expressions to get at the exact answer. Sometimes the calculator, like I said, will kind of get you there and give you an exact answer, and sometimes it can't quite find the closed form simplification for these things, so just kind of be mindful of that. And like I said, this is a really intense and hard problem. So the idea of having to make a substitution involving a trigonometric identity here is a hard problem. So, don't expect like your final exam to have 5 of these. Like usually the final exam has 1 of these because these are just inherently hard to do. So yeah, I mean, like your assignment might have a couple of them because, I want you to practice them before the final exam. But, these things take a lot of time, right? It took us like probably a full lesson just to talk about this particular example, set it up and execute it, right? It takes a long time to do these by hand. And they're also questions where they're very potentially frustrating because if you make a small error along the way, it really sets off this like domino reaction where things get way out of hand and kind of crazy. So these are types of questions where I highly recommend, putting it into the integral calculator, have the integral calculator rifle off the solution, and then try to do it on your own, right? And if you kind of get stuck or you want to check your work, you have at least a reference point. You can have that integral calculator show you the steps of how to start the problem. So that's my recommendation for working with these kinds of substitutions. And what I want to do for the rest of this like smaller class is talk about the general strategy for setting up a trigonometric substitution like we did in that last example. Okay, so this is the Trigonometric Substitution section from the textbook. It's inside the it's like the Integral Tools chapter, or the techniques, I think is what it's called, integration techniques. It'll be one of the big techniques inside of that chapter. So trigonometric substitutions. Essentially what we want is to be able to simplify integrands having a square root. Now, the one that we looked at was something of the form a squared plus x squared, or like something squared plus something squared under the square root. So that's one common form that comes up. So if I kind of go back and I take a look at the arc length problem, the original integrand that we kind of came up with was this one, right? This one that was one, like something squared plus a variable thing squared under the square root. So a number plus a variable thing squared. So that's one kind of common square root that could come up. Another common one that could come up is we have the number portion, and then we have a subtraction of a variable portion. So we have like 1 minus x squared, or like 1 minus 4y squared. So these kinds of things come up quite often. And then the last possible case we could get is we could get the variable portion first, and then subtract the numerical portion. Okay, so we could get like a 4y squared minus 1. So these are the three possible cases. Notice that, if I swap the order here and I did the variable portion plus the numerical portion, these are really just the same. Right, so whether or not we have the number plus the variable bit or the variable bit plus the number bit, we're going to be using the same kind of substitution to tackle these problems. So these are the special kind of integrands we're looking for. If it looks like they're in this form, then we can use a trigonometric substitution to tackle these integrands. Now, this is a special kind of trigonometric substitution. It's a little, I would say, it's going to feel slightly different, I think, than a regular U substitution, because in a U substitution, or the substitution that we've talked about earlier in our course, usually we're looking to see if the derivative is also inside of the integrand. Where here, we just have a square root. So it's almost like a special class of substitution where our goal is to turn the expression into something squared so that we can get rid of the square root. So it's less about looking to see if the derivative of u is there, and more about setting it up in a way to remove the square root. So it is a substitution, so we're going to do a change of variables. It's just a special class. It's going to feel a little bit different than our usual substitution. Now, I want to recall our three Pythagorean identities. So, let's see. We have sine squared. Let's go sine squared. Let's use theta here as our different variable. So, sine squared theta plus cosine squared theta is equal to 1. Now, this essentially is like a variable squared plus a variable squared equals 1, equals our a squared. That's not really the form that we want. So what we would like to have is like a numerical plus a variable, or a numerical minus a variable, or a variable minus numerical. So sine squared plus cosine squared doesn't have that until we rearrange the form a little bit. And typically what we do is we rearrange it in the following way. We're going to rearrange it to 1 minus sine squared is equal to cosine squared theta. And so now we have something that's like a numerical thing minus a variable thing. Okay, so this is going to line up with this one here. So 1 minus sine squared is typically how we want to think about an integrand that has an a squared minus x squared. And so now I want to think about, so this is going to be for number 2. And now I want to think about, well, we have a squared minus x squared. So I'm going to multiply all 3 terms here by a squared. That's going to get us a squared minus a squared sine squared theta is equal to a squared cosine squared. And that reveals to us what we want to make for our substitution. So what we want to make for our substitution is we would like x squared to look like a squared times sine squared. Okay, so we would like these two things to be the same. Okay, so that's how we deal with integrals that look like a number squared minus x squared. We're going to set up the substitution to look like x squared equals a squared sine squared. That should allow us to remove the square root by replacing some stuff with a squared cosine squared. Okay, so that's going to get rid of the square root for us. This also sets up the differential in a nice way too. And we'll look at a couple examples of how to get at the differential dx. We basically just kind of use this expression here to solve for x, take the derivative, and then figure out how to replace dx with something in terms of, let's say, d theta. So that's how we tackle the first one. So I would say, you somehow want to make a note to yourself that, if I see something that looks like this, the substitution that I want to think about looks like this. Those two things always go hand in hand. Okay, so that's the first kind of Pythagorean identity. But we have two other Pythagorean, well, actually one. The one other one I think is going to solve the rest of the cases, and I think that's our tan identity. So we know that tan squared theta plus 1 is equal to secant squared theta. Okay, so right now we have a variable portion plus a numerical portion. That does solve number 1, right? This is going to help us think about this first one. Okay, so let's kind of roll through this one and kind of see how we kind of intuitively make sense of this one. So number 1 is, I'm going to write it as x squared plus a squared. And what we have is the following. We have this variable portion. We have this sorry, I need to multiply by a squared first to make everything line up. Okay, and now we have something that kind of looks like the thing that's underneath the square root, right? I have a variable thing plus a squared. Okay, so it kind of looks like the thing that we want. And what we want to do now is we would like to make this and this be the same. Right? We would like, if x squared was really a squared tan squared, I could replace this whole thing under the root with a squared secant squared and then essentially remove the square root. So this kind of sets up our substitution. In this case, we need x squared to be equal to a squared tan squared theta. Okay, so if I ever see an integral that looks like this, this is the substitution that we want to think about. Okay, I want to think about a tan kind of substitution. Okay, and the last kind of integral is this one where we have the variable portion minus the numerical portion. And we're just going to rearrange the tan bit here. So we know that tan squared theta is equal to secant squared theta minus 1. Okay, so now we have something that's like a variable thing squared minus a numerical thing squared. And same story, let's multiply by a squared to make this look a little bit more legit, like the thing that we're solving. And that should be an a squared here. And so now we want this variable portion thing to look like this variable portion thing here. And that leads us to the change of variables. X squared is equal to a squared secant squared theta. Okay, so in other words, anytime I see an integrand that looks like a variable thing squared minus a numerical thing squared, I should be thinking about doing a secant kind of substitution. So that's it. It kind of boils down to these 3 different cases. So I would just, I would write these down on like a little cheat sheet for yourself, so you have them for quick reference. And what we're going to do is we're just going to work through a couple examples here of how to set up these kinds of problems. We're not going to fully execute them because we need a little bit more tools to be able to fully execute, but I can at least show you a couple examples of how to set up these things. Okay, so that is where we're at next. Okay, so what we're going to do is we are going to determine I don't want to say the appropriate, like we want to determine a trig substitution for the following. So the ones I've given you are the standard ones, but there are other possible substitutions that will work. But you really just need to memorize these 3. So if you want, you can play around a little more with the other trig identity, which is the cosecant and cotangent identity, and you can find some substitutions using that identity as well that are going to help. But these are the 3 that the textbook's going to go over, and the textbook chooses these 3 because the derivatives of x are not going to have any negative signs, right? The derivative of sine is cosine, the derivative of tangent is secant squared, and the derivative of secant is secant tan. So it's quite easy to find these derivatives, the differentials dx, without the need to multiply by a minus 1. So that's why these 3 are typically chosen to be the standard ones. So determine trig substitution for the following. Okay, so we're going to determine a trig sub, and we're going to simplify that square root out. The resulting integrand is going to be what we call a trigonometric integral, and that's where we're going to stop for now. And I'll give you some more strategies after reading week to solve some of the resulting trig integrals that might pop out from working with these substitutions. So let's look at the following. Let's do x cubed and then x squared minus 25. Okay, I don't think we're going to need that today. Okay, so when I look at a problem like this, and I see a square root that is a squared thing plus or minus a squared thing, my first instinct is to think about doing a substitution in order to get rid of the square root. In this case, we might also be able to do a regular u substitution and make this work. Yeah, I think we can probably do a u sub as well. So I might show you both cases here, but let's try to find a trig sub because that's what the example wants us to do. So let's look at this, and we're going to kind of scroll back up to our 3 possibilities and figure out which one of the possibilities we have. So Do we have something like number 1? Do we have a variable thing squared plus a number thing squared? No. Is it something like number 2, which is a number thing squared minus a variable thing squared? No, the variable comes first. So this is like a number 3 kind of integrand. I have the variable thing squared minus the squared number thing. Okay, so this is like a type 3. This implies that we should think about x squared, the variable portion of this, as a squared secant squared theta. Now, what is a squared in this case? Well, a in this case is 5, right? So a squared is 25, so a is equal to 5. We're going to take the positive root here just to make things a little simpler. Okay, so our substitution is x squared is equal to 25 secant squared theta. Okay, and that's how we want to start this particular problem. Okay, once we have this, we are going to apply the square root. Okay, so we know that x is equal to 5 secant theta. And then we're going to take the derivative, because we're going to need to replace this dx with something in terms of d theta. So dx with respect to theta is 5. The derivative of secant theta is secant tan. Okay, so dx can be replaced with the expression 5 secant theta tan theta times the differential d theta. Okay, that's the hard part, I think. The hard part is figuring out how to get the substitution to work and figuring out what your dx is going to look like. Now it's just a little bit of algebra with like dealing with powers and stuff like that. So what is x cubed? Well, x is 5 secant theta. So x cubed must be 5 cubed secant cubed theta. Okay, so maybe I'll just write that in red. Okay, so x cubed is 5 cubed secant cubed theta, right? And I'm going to get that from this relationship here. Okay, now let's deal with the root. We know that x squared is 25 secant squared. Okay, so there's the substitution for x squared. And finally, we need the substitution for dx. I'm kind of slowly running out of space here. Just let me move this over a touch and see if that will help. Okay, so dx is 5 secant theta tan theta d theta. Now, this right now looks much worse than what we started with, but it's not, because it is going to simplify into something not as terrible as the original thing. Okay, 5 cubed is 125. Secant cubed times, well, actually this is going to be 5 to the power of 4, right? I have actually 4 copies of 5, so that's 625. I have a secant cubed and another secant, so we're going to get a secant 4 theta. And let's just put this tan theta here for now as well. Okay, underneath my square root, I'm going to have 25 times secant squared minus 1. Secant squared minus 1 is tan squared. So underneath the square root, we're going to get 25 tan squared theta. This is the whole point of doing this particular substitution with secant, so that we can get rid of the square root. Okay, just a little bit left here to do cleanup-wise. So 625. This is going to turn into 5 tan theta after I apply the square root. So what's 625 times 5? That's a big number. That is 3,125. 3,000. Oops. Let's go back in black. Okay, we're going to be left with 4 copies of secant, and we're going to get 2 copies of tan d theta. So that's where we're going to stop for now, because we don't Well, I mean, we could continue on, but this is kind of where I want to stop. I want you guys to get used to setting up the problem, understanding how to get rid of the square root, and being left over with a resulting integral that just has trigonometric functions to some kind of power. So that's going to be the end result, just trying to get a trig function that has, some secants and tans to a certain power, some sines, cosines to a power, or something that looks like that. And we'll deal with kind of more generalized approaches for these after the break. If you do want a challenge, these are all solved for the most part by trying to find a good substitution. So trying to either take u equals secant, u equals tan, or u equals secant tan, something like that. Some kind of combination of these should hopefully work. So if you want a little challenge over the reading week break, see if you can finish this up using a clever substitution, a clever u substitution. Okay, so a more standard substitution like what we saw at the beginning of the course. Just timing wise, because I want to cover at least one more example with you here. I'm not going to do this one using a typical substitution, but I do think that if you put this into the integral calculator, you might be able to do a little bit of an easier reroute through this question by doing a u substitution right off the bat. So you can always try that as a little extra homework assignment too. See if you can set this up without having to use trig substitution, because I think that's going to be a little bit easier to do. But for now, let's look at a second example, just so that we have another one for our notes here. What did we do? We did an x minus something. So let's do an integral that has a number minus an x squared. Okay, so we have a fraction. In the numerator is 9 minus x squared, and in the denominator is x squared. So like before, we want to kind of look at this root and try to determine what class of root is it. Is it a type 1, type 2, or type 3? So this one looks like it's going to be this kind of integral. It has the number portion first, then the subtraction by the variable portion. So it looks like we're going to try to set up a sine substitution in this case. This is a type 2 kind of root. So x squared, let's make that equal to a squared sine squared theta. Now, what is a squared? We know that a squared is equal to 9, okay? Or a is equal to 3. So I'm going to put that in here as well. So we know x squared is equal to 9 sine squared theta. Applying the square root, we get 3 sine theta. And then the last step is to figure out what this dx is going to turn into. So I'm going to take the derivative here, which is 3 cosine theta. So it looks like we can get rid of dx by replacing it with 3 cosine theta d theta. And now we're pretty much good to go. We have all the pieces that we need in order to get this question rolling. So we are going to take this square root. We're going to replace x squared with 9 sine squared theta. In the denominator, x squared, we know that that is 9 sine squared theta. Dx, that becomes 3 cosine theta d theta. Okay, so here's our substitution using that x squared equals 9 sine squared substitution. Okay, now our goal is to try to simplify this square root and hopefully get a resulting integral that has only maybe sines and cosines inside of it. So let's take a look at this integral, or this square root up top. So this should be 9, and then we're going to get 1 minus sine squared. 1 minus sine squared is cosine squared. Okay, that's going to allow us to get rid of the square root. So in the numerator, we're going to have 3 cosine theta. Denominator, 9 sine squared theta. And our last step here is just to kind of simplify this a little bit as best we can. So it looks like our 3, 3, 9, those are going to cancel out and give us 1. And here we're going to get integral of cosine squared theta over sine squared theta d theta. And that's commonly known as not tan, that's cotan, I think, right? That's cotan squared theta. So we've simplified this, and can we integrate cotan? Do we know how to do that? Cotan squared. I don't think we can actually integrate cotan squared, to be honest. Not easily. Right, I can't integrate tan squared. Okay, yes. So I'm just kind of stumped. I'm not sure exactly how I want to proceed with this, but one of these forms is good for simplification. This is essentially where I want you to be comfortable getting down to after this particular lesson. So understanding how to find the type of substitution that we need and understanding how to execute that substitution. So that's what I want you to work on over the reading week, so that when we get back, we can talk about how to tackle these resulting integrals like secant 4 tan squared. How do I start integrating something like that? Or cotan squared, how do I integrate something like that? Maybe we're going to be forced to use a reduction formula or something like that. Or maybe we can use the cosine sine integral and maybe find a substitution that would work. So yeah, so that's what we'll talk about after reading week. Hopefully that gives you a little bit better of an idea of how to get at these substitutions. That was kind of the goal of this lesson, was identify the square root, and it really boils down to 3 possibilities, right? So I just want you to be comfortable identifying the root, figuring out what that substitution looks like, and then just plugging it in and trying to simplify. So, have a go in the trig substitution section. Try to identify that sub, try to simplify those square roots. Just do, 3 or 4 of those over the reading week, just to make sure you're comfortable doing this, okay? And of course, have a lovely reading week, guys. Remember, if you're watching this on Friday, that the quiz is due by the end of day on Friday, so by midnight. And the second assignment, which will not cover trigonometric substitution, will be due by Sunday at midnight of the reading week. So I believe that's the 21st of February. Yep, so by the 21st, I want assignment number 2 completed. And then we'll start fresh with some new stuff on the 22nd. Okay, have a great rest of your morning, afternoon, night, whatever it might be where you are right now. And I will see you after reading week. All right, take care, guys.